So we start this lecture and we want to compute first the drift speed of some electrons. So say you want to compute it in a copper wire, and this copper wire has a cross section area of 1 into 10 to the power of minus 7 meter square. The current flowing through the wire is 1.5 amperes. The atomic mass of copper is 63.5 AMU. And the density of copper is 9 into 10 to the power of 6 grams per meter cube. So you know the atomic mass of copper is 63.5 AMU. So that means there are 6 into 10 to the power of 23 atoms in 63.5 gram of copper. So this 6 into 10 to the power 23 is Avogadro number. So these many atoms are always there in the atomic mass of that element. So say N is the charge carriers per unit volume. So we will assume that each atom contributes an electron which will carry the charge. So the charge carriers per gram would be 6 into 10 to the power of 3 divided by 63.5. So these many atoms you would have per gram, or these many charge carriers per gram. Now you multiply this by the density, which is gram per meter cube. So you have 63.5 grams in the denominator. So this is charge carriers per gram. So G and G cancel out. So you get charge carriers per meter cube. So this is equal to 8.5 times 10 to the power of 28 charge carriers per meter cube. Since this is a copper wire, the charge carriers are nothing but electrons. In case of charged gases, this could be charged molecules. So now we write down the formula for drift speed from the previous lecture. Vd is equal to I over NEA. Now we just plug in the values. Now E is the fundamental basic charge, and this you know to be E is 1.6 into 10 to the power of minus 19. And the area is also given us as 1 into 10 to the power of minus 7. So this will become equal to 1.1 times 10 to the power of minus 3 meters per second. So notice that the speed with which electrons move is very low. So electrons are moving very slowly, but we still say the current passes instantaneously or at the speed of light. Now why is this so? That is because as soon as you apply electric potential, the electrons at the end of the wire start moving out immediately, and that is why the current starts flowing instantaneously. So you are talking about flow of current as electrons coming from the ends of the wire. So the time taken for the electron to go around the wire is not important, but the electron comes out instantaneously from the end of the wire. Now we want to talk about Ohm's law. So Ohm's law states that ratio of current density, so we will denote this by J, to the electric field E is a constant. So that is J over E equals to sigma. So sigma is a constant. So this is called conductivity for a particular conductor. So this equation is Ohm's law. Now I'm going to write J as I over A because J is current density, I is current, and A is the area of the cross section of wire. So say if you have a uniform electric field, then the potential difference across two ends of a wire so this is given as, so this is the wire, it has two ends, the length of the wire is L, you have I and electric field both in the same direction. So the potential difference is given as, you integrate across the length of the wire, E vector dot product with dl vector. So you write that E vector dot dl vector as E dl cos theta. Now cos theta will be 1 because theta is 0. So electric field is in the same direction as the length of the wire. So you take E out, so this becomes E times L. So you can rewrite this, delta V is equal to EL, or E is equal to delta V over L. So you can plug this into the Ohm's law. So the Ohm's law is right here. Let's mark this in red because it is important. So you get J over, instead of E write delta V by L, is equal to sigma. Or you can rearrange this and you can get delta V is equal to JL over sigma. So J is I over A, plug it in, you get I over A sigma times L is equal to delta V. So you can rewrite this as L over A sigma times I, and you rename this term L over A sigma as R. So this R is called resistance of conductor. So now you have delta V is equal to R times I. This is a very important equation. Now R is called resistance of conductor. So the unit of R is ohm. So let us mark this very important result. This we will keep using again and again. So R you can rewrite as delta V over I. So delta V is measured in volts and I is measured in ampere, and the units of R are ohm, and the symbol which we have written there is omega. The omega symbol, that is ohm. So these are units of R. So let us rewrite this. So if you say that if 1 volt of potential difference causes a current of 1 ampere to flow through the wire, so 1 volt of potential difference causes current of 1 ampere to flow through the conductor of the wire, then the resistance of that conductor is 1 ohm.